You might be wondering why bother with twinLab when you could make predictions with other available tools. twinLab simplifies the complex world of Bayesian inference and Gaussian processes, making it accessible even to those without an extensive background in mathematics or data science. Welcome to twinLab, I'm Anna, and in today's video we're going to explore Predict in twinLab, a powerful tool to facilitate modeling tasks within the twinLab ecosystem. By the end of this video, you'll be equipped with all the knowledge and necessary tools to confidently use Predict. Make sure to check out the full written tutorial that accompanies this video on the twinLab website, when you can dive deeper into Bayesian inference and Gaussian processes. You'll find the link in the description below. Plus, you can download other additional resources. Now let's break down what to expect in this video. In this tutorial, we explore how the model Predict works under the hood. Then, we will demonstrate how to train an emulator on a dataset with one input variable and one output variable. Finally, we will cover how to train an emulator when we have a high-dimensional problem. You can learn more about twinLab's capabilities and request a demo on our website. You can also learn more about Gaussian processes by watching our series Understanding Gaussian Processes. So without further ado, let's start learning. Hit that like button and don't forget to subscribe for more twinLab tutorials. Let's get started. The Predict module uses the power of Gaussian processes, Bayesian inference, and uncertainty quantification techniques to provide reliable predictions and insights for various predictive modeling tasks. Users provide input data containing features and corresponding target variables, which is the desired output. During training, the Gaussian process learns the underlying patterns and relationships in the data. Once the model is trained, users can make predictions for new input data points. In addition to predicting the mean response, the Gaussian process also provides uncertainty estimates for each prediction. This uncertainty quantification is a key feature of Gaussian processes, allowing users to assess the reliability of the predictions. Bayesian inference techniques are used to update the model's beliefs about the underlying function based on observed data. This allows the Gaussian process to make informed predictions that incorporate both prior knowledge and new evidence. The Predict module also includes optimization algorithms to optimize the Gaussian process model. In this example, we're going to demonstrate how to train an emulator on a dataset with an input variable and an output variable. Right, so first we're going to import the required libraries. These are going to be print, numpy, pandas, matplotlib, and twinLab. You're also going to need to set up your API key. Also remember not to share your API key with anyone or in any repositories in order to maintain security. In twinLab, datasets must be either in the form of a pandas data frame object or as file paths pointing to CSV files that can then be converted to a pandas data frame. And it's very important that both formats have clearly labeled columns. So specifically, the input variable should be labeled as X and the output variable should be labeled as Y. Data in twinLab is expected to follow a column feature format where each row represents a single data sample and each column represents a data feature. Okay, so in order to generate our data, first we're going to import random for generated random numbers. Then we're going to define the length of the lists, which is going to be 10. And then we're going to generate random numbers for the list X and then for the list Y. Then we're going to create a data frame using pandas where the X column corresponds to the values in the list X and the Y column corresponds to the values on the list Y. And finally, we're going to display the content of the data frame to visually inspect the generated dataset. Just keep in mind that because we're using random points, your dataset might look a little bit different. twinLab offers a dataset class equipped with attributes and methods for processing, viewing, and summarizing datasets. To access datasets in twinLab, they must be created with a dataset_ID, which serves as the identifier for accessing them. Datasets can be uploaded into twinLab using the upload method. So we're going to define the name of the dataset as example data, using the variable dataset_ID. Next, we're going to initialize a dataset object named dataset with the specified dataset identifier. Then we're going to proceed to upload the dataset into the twinLab environment using the upload method of the dataset object with the parameter variables true, so we can see the process of uploading in detail. And what we get in the output is the data frame is uploading, processing dataset, and finally dataset example data was processed. The emulator class is responsible for training and using surrogate models. Similar to datasets, we assign an identifier to the model, which is how it will be saved in the cloud. And to actually train the model, what we do is to utilize the emulator.train function. So we're going to set the name of the emulator as example emulator by assigning it to the variable emulator underscore ID. And then we are going to create an instance of the emulator class named myEmulator with the specified identifier. We're going to use the train method of the myEmulator object, providing the dataset we want to train the emulator on, along with specifying the input variable X and the output variable Y, using the inputs and outputs arguments respectively. So now the surrogate model is trained and saved to the cloud under emulator ID, and now it can be used to make predictions. So we're going to define the inputs for the dataset using NumPy, and we're going to create an array containing 128 evenly spaced values between 0 and 1. We're going to convert this array into a data frame, which we're going to call df_eval, and then we're going to display the data frame just to inspect the generated input data. Then we're going to utilize the train emulator, myEmulator, to predict the results for the input data contained in our evaluation data frame. Then the predictions are going to be obtained using the predict method of myEmulator. And after that, we're going to concatenate the predicted mean and standard deviation values into a single data frame, which is going to be the result data frame along with the column axis. And finally, what we're going to do is we're going to extract the mean and the standard deviations for this data frame and convert them into NumPy arrays before printing the first few rows of results data frame to observe the first few rows of the predictions. So the prediction mean is the expected prediction for each data point, and the prediction standard deviation indicates the level of uncertainty associated with each prediction. So together, these two components provide a valuable insight into the model's prediction. The prediction mean gives you a central estimate, while the standard deviations offer a measure of prediction reliability. A higher standard deviation suggests greater uncertainty, while a lower standard deviation implies a more confident prediction. Now we're going to visualize our predictions. So we're going to use the train emulator to create a plot where the x-axis represents the input variable, which we have labeled as x, and the y-axis represents the output variable labeled as y. We're going to set the x-axis limits between 0 and 1, and we're going to overlay the data training points represented as a red scatter points. And we are also going to add a legend to the plot to distinguish between the emulator predictions and the training data, and then we display the plot. And this is what we get. So we can see that this is what the emulator has predicted, and this is our big band of uncertainty with the training data represented in these red dots. Let's talk now about how to sample from the emulator. The emulator.sample function can be used to retrieve a number of results from your model. It requires the inputs for which you want the values and how many outputs to calculate for each. So again, we're going to define a set of sample inputs, and for that we're going to create an array containing 128 evenly spaced values between 0 and 1, and then we're going to convert it into a data frame. We are going to specify the number of samples that we want to calculate, and in this case we're going to set it to 100, and we're going to store it in the variable number of samples. Using the train emulator, we're going to calculate the samples for the provided input data, generated 100 samples for each input point. The results are going to be stored into sample_result. We're going to display the results of the sample calculations using the display function. This data frame contains the sample outputs generated by the emulator for each input point specified in the sample inputs. The sample result data frame provides insight into the variation and distribution of the emulator's predictions across the range of input values provided. Now let's see how we can plot these results. So we're going to set up parameters for plotting. We're going to define colors for curves and data points, setting the transparency level, and then we're going to specify whether to plot training data and model bands. And in this case, we're going to set the plot training data equal to true and the model bands equal to false. But if you want to visualize it, you just want to turn it to true. Then we're going to plot the sample results generated by the emulator for the given input data. We limit the x-axis to the range between 0 and 1, and we are going to add a legend to the plot and display it. So what we can see is a visualization of both the training data and the samples drawn from the model, allowing for a visual assessment of the emulator's performance and the distribution of the predictive values across the input range. Finally, let's talk about how to delete the emulator and the dataset. We can use .delete to remove the emulator object that we have previously created, and we can also use .delete to delete our dataset. Deleting these objects is a really good practice as it ensures that no unnecessary resources are retained. In many real-world situations, it's not just only one factor that's influencing the outcome. There are often several. Imagine that you're trying to predict temperature. You know that there's just not one thing that affects it. It could be humidity, but it could also be location, it could also be time of the day, and more. twinLab recognizes this complexity and makes it easy to handle. With just a small tweak to the code we've already seen, you can model these relationships between multiple input variables. The only portion of the code that needs to be modified is the following. So in the input, you specify all the input variables you want the emulator to consider when making the predictions, and you just list them inside the square brackets, separating each variable's name with a comma. And this concludes the predict tutorial. Don't forget to like and subscribe to be updated with our latest tutorials and upcoming content. Make sure to download the video resources on the DigiLab website, where you can also find more courses on data science and AI. You can also find the written tutorial linked in the description. Thank you so much for joining me in this journey. I can't wait to see you on the next one.